nobody knows exactly what the first human words sounded like. And that fact alone should stop you cold for a moment. Language is so fundamental to what we are that imagining human existence without it feels genuinely impossible. Every thought you have ever had was shaped by language. Every relationship you have maintained depended on it. And yet, at some specific moment in deep prehistory, none of it existed anywhere on Earth. There was no word for fire, no word for danger, no word for love, no way to say any of it at all. And then gradually, incompletely, over tens of thousands of years, something extraordinary began to emerge. The question of when humans first started truly talking is one of the most contested in all of science, not because researchers lack interest, but because language leaves almost no direct trace in the fossil record. Spoken words vanish the instant they are produced, leaving nothing behind for any future archaeologist to find. The challenge is compounded by the fact that we cannot simply dig up a conversation the way we dig up a bone or a tool. What we have instead is a collection of indirect evidence, biological clues, and competing theories that illuminate different pieces. The biological story begins with anatomy, specifically the evolution of a vocal tract capable of producing complex speech sounds. Modern humans have a descended larynx sitting much lower in the throat than in any other living primate. This anatomical arrangement allows us to produce a much wider range of vowel sounds than our closest living relatives. But it also makes us uniquely vulnerable to choking on food in a way that no other mammal regularly experiences. Evolution does not preserve anatomical features that only cause problems without providing compensating benefits of significant value. The fact that we retained this dangerous arrangement strongly suggests that complex vocal communication was worth that considerable cost. The hyoid bone, a small horseshoe-shaped structure in the throat that anchors muscles used in speech, provides another clue. A Neanderthal hyoid bone discovered in Blombos Cave in Israel in 1989 was virtually identical in shape to modern human hyoids. This finding suggested that Neanderthals may have had the anatomical capacity for speech of some kind, at least in terms of throat structure. But anatomy is only part of the story because the brain structures required for language are equally important and harder to detect. Broca's area and Wernicke's area in the modern human brain are the two primary regions most associated with language production and comprehension. Endocasts, which are casts made of the interior of ancient skulls, can sometimes show impressions left by these brain regions. Evidence from endocasts suggests that language-associated brain regions may have been enlarging in hominins as far back as 2 million years. But having the brain hardware does not necessarily mean the software of grammar and vocabulary was running on it immediately. The genetic evidence adds yet another essential and deeply fascinating dimension to this already complicated picture of language evolution. In 2001, researchers identified a gene called FOXP2 that appears to play a crucial role in the fine motor control required for speech. Humans with mutations in this gene have severe difficulties with the precise muscular coordination that spoken language requires. The human version of FOXP2 differs from the chimpanzee version in just 2 specific amino acids out of several hundred, but those 2 differences appear to be profoundly important for the kind of precise articulatory control that speech demands. Remarkably, Ancient DNA analysis has shown that Neanderthals carried the same human version of FOXP2 that modern humans carry. This finding suggests that whatever FOXP2 does for language, Neanderthals had at least this particular piece of the genetic puzzle. The archaeological record provides a third line of evidence that is both more visible and more interpretively complex. Symbolic behavior, the ability to assign arbitrary meaning to objects and representations, is closely linked to language in cognitive terms. When ancient humans began producing art, jewelry, and ritual objects, many researchers interpret this as evidence of language-capable minds. The Blombos Cave site in South Africa contains some of the oldest evidence of symbolic behavior, dating to roughly 75,000 years ago. Researchers found engraved geometric patterns on ochre, pierced shells that may have been worn as beads, and other evidence of symbolic thinking. Some researchers have argued for even older evidence of symbolic behavior going back 100,000 years or further in scattered sites. But there is an important and frequently debated distinction between symbolic capacity and the fully recursive grammar of modern language. You can have simple referential communication, essentially pointing and grunting with some consistency, without having anything like modern syntax. The question is not simply whether ancient humans communicated, but whether they had the specific grammatical structures that make language uniquely powerful. Modern human language is recursive, meaning it can embed clauses within clauses to create sentences of theoretically unlimited complexity. What these sites demonstrate is a mind already capable of living in a symbolic world of meaning and shared reference. This allows us to talk about events that happened long ago, things that might happen in the future, and things that have never happened at all. A bee dance communicates direction and distance with remarkable precision, but cannot discuss yesterday or speculate about next week. The capacity to think and communicate about abstract hypotheticals, about what might have been or what could be, may be the real cognitive revolution. Linguist Noam Chomsky has argued that the critical innovation was a single cognitive operation called merge, the ability to combine elements recursively. This single capacity, according to Chomsky, is what distinguishes human language from every other communication system on Earth. When exactly this capacity appeared in the human lineage remains deeply uncertain and the subject of genuinely fierce academic disagreement. One influential view associated with researchers like Chomsky and Richard Lewontin argues that language appeared relatively recently and suddenly. In this view, a single genetic mutation, approximately 50,000 to 70,000 years ago, triggered the cognitive revolution visible in the archaeological record. The sudden flourishing of complex art, long-distance trade, and sophisticated tools after this period reflects genuine new cognitive capacity. An opposing view argues that language evolved much more gradually over hundreds of thousands of years through incremental improvements. In this gradualist model, there was no single moment of language invention, but rather a slow accumulation of communicative sophistication. Each generation passed on slightly more complex communicative habits to the next, building over immense timescales without any single breakthrough. The truth almost certainly lies somewhere between these poles, with different components of language evolving at different rates and times. There is also the question of gesture, which some researchers argue preceded speech as the primary channel of early language. Modern great apes show impressive capacity for learning gesture-based communication systems in ways they simply cannot do with vocal speech. Chimpanzees and gorillas raised with human contact can acquire substantial vocabularies of signs and use them in genuinely meaningful ways. The same animals cannot produce anything resembling human speech regardless of how much training and encouragement they receive. This asymmetry suggests that our primate ancestors may have had gestural communication systems that preceded the full development of vocal language. The mirror neuron system, which fires both when performing an action and when observing someone else perform it, may have been critical in this transition. Mirror neurons could provide a neurological bridge between action and meaning, allowing the observation of others to directly activate understanding. Michael Corballis at the University of Auckland has argued extensively that language evolved from a gestural system that gradually became vocalized. In his model, speech did not replace gesture, but rather joined it as language evolved to use both channels simultaneously and complementarily. This would explain why modern human language remains deeply intertwined with gesture in ways that people who cannot see each other still use. People gesture when talking on the phone, when describing things to blind conversation partners, when alone talking to themselves. The coupling of gesture and speech appears to be so deep in human neurology that separating them requires deliberate and conscious effort. There is one more dimension of this question that deserves specific attention because it concerns not when language evolved, but how it spread. If language capacity evolved once in a single ancestral population, we would expect all human languages to share certain deep structural features. And remarkably, they do, in ways that go beyond superficial similarity to suggest constraints imposed by human cognitive architectures itself. This neural overlap between observing and doing may have been the evolutionary foundation on which shared meaning was first constructed. Joseph Greenberg spent decades cataloging what he called language universals, features shared across thousands of languages with no common ancestor. Nearly all languages place subjects before objects. Nearly all have pronouns distinguishing at least singular from plural references. Nearly all have ways of marking basic distinctions in time, space, and the relationship between actors and actions in the world. These universals suggest that human language is not a purely cultural invention that could have taken any form at all. It is shaped by the specific architecture of the human brain in ways that constrain what any natural language can look like. The linguist Derek Bickerton introduced the concept of a language bioprogram, an innate template that shapes the acquisition of any language. Children everywhere acquire language on roughly the same developmental schedule and make similar types of errors regardless of which language they are learning. These regularities suggest something deep about the biological substrate that makes human language possible in the first place. Creole languages, which emerge when speakers of multiple different languages need to communicate and create a new shared language, show a remarkable tendency to develop consistent grammatical structures, even when the speakers had no common grammatical tradition to draw on. Bickerton argued this showed the language bioprogram expressing itself when cultural grammatical traditions were absent or unavailable. So what did the first human language actually sound like? And can we reconstruct anything about it with any real confidence? The comparative method in historical linguistics allows reconstruction of ancestral languages through systematic comparison of related modern languages. This method has successfully reconstructed Proto-Indo-European, the ancestor of languages from English to Hindi, spoken roughly 6,000 years ago. But this represents only a tiny fraction of the time that language has existed, and the method breaks down over longer timescales. Beyond about 10,000 years, the sound changes that languages undergo become too numerous and too complex to trace back reliably. Joseph Greenberg attempted a more ambitious reconstruction, arguing that all human languages share a common ancestor he called proto-world. The very fact that children with no instruction spontaneously develop communication systems with grammatical properties is itself remarkable evidence. The idea remains controversial, and most historical linguists consider it unworkable given the timescales and the limitations of available methods. What we can say with more confidence is that the first language was almost certainly not as simple as a few grunts or isolated calls. The archaeological evidence from Blombos Cave and other sites suggests that humans 75,000 years ago were cognitively sophisticated enough for complex language. The biological evidence from hyoid bones, FOXP2, and brain anatomy suggests the necessary hardware was in place for Neanderthals and archaic humans. The universals research suggests that whatever the first language sounded like, it was constrained by the same cognitive architecture we still carry. The gesture research suggests it may have been more visually embodied than modern spoken language typically appears to casual observers. Perhaps most significantly, the very fact that we are still asking this question tells us something important about language itself. Language is the tool we use to investigate the origin of language, which creates a kind of deep recursive puzzle at the heart of the inquiry. We are using the thing we are trying to understand in order to understand it, which is either deeply frustrating or remarkably beautiful. Perhaps both, depending on which words you choose and how you arrange them, which is, of course, the entire point and the entire miracle.